works at Amazon, doing their job. She was like, oh, I can give you a referral. It's been so yeah.
对，你知道，然后我走到那里的时候，他想到我在懂你的意思，然后就立刻被记存到。
Okay, welcome back to EE631. So today I'm pretty sure we're gonna finish the signal processing topic, which means that your first homework should be coming. So I'll ask the TA to post the first homework after this class. Okay, so today we're gonna continue what we left on Monday. We're gonna talk about, once you convert the signal into discrete time domain, how do we change the sample rate? Okay. So this is what we call the sample rate conversion. All right. So the first one is called downsampling. So essentially, what we are doing is that discrete time signal, you take a bunch of samples. The downsampling just means that you want to reduce the number of samples. How do you reduce? So you're gonna keep one sample every m samples. So every m samples, you only take one. So let's look at the scenario. Since we talk about A to D conversion. So let's say you have ADC and the output, you take all the sample x of n, and this ADC will be sampled at f clock. Okay, so let's say ADC will perform the sampling at the rate of f clock. So now we're gonna downsample, right? And as I said here, we're gonna take one sample for every m samples, right? So usually this is how we write. We just do a down error by factor of n. Okay, so whenever you see this, that means that you have downsample. After you downsample, right? So your input is a discrete time signal. After you downsample, the output is still a discrete time signal, right? So they're all by samples. So I'm gonna call that as xd of n. So d is downsample. And because I take one sample for every m samples, so effectively, my sample rate right now is f clock divided by m. So let's try to visualize this, right? So as I said, your input is a bunch of the discrete time signals like this. If I decide to downsample, I may take one. For example, every 4 sample I take one, it will be like this. And maybe that's another. Okay. So that's how you do downsample. So still a discrete time signal, it's just that the sample is a lot less. So so this in the time domain view, the question that we always ask ourselves is that because we care about the time domain and the frequency domain view, right? So what happened after we do the downsampling? What happened to the spectrum? All right, so I'm gonna call the original discrete time signal, as we derived before. This is nothing but a shifted copy of the original analog spectrum, right? And it will be repeating as integer multiple of the sampling frequency, omega s. And this k will be from -infinity to infinity, right? So every shift copy of the sampling frequency, you're gonna see the original analog signal spectrum x of omega. Okay, so now let's do downsampling. So xd of n mathematically is equal to x of n times n. Does that make sense? you see when n equal to n is equal to x of m, and when n equal to 2, it's correspond to x of 2m, right? So every m samples, you're gonna take one. Okay, so that's the math. Okay, so if you look at the frequency spectrum, when you do a discrete time Fourier transform, if I scale the time domain by a factor of m, what happened to the DFT output? So the DFT output, xd of omega, will be equal to, so how do we scale? So if I multiply by in time by a factor of m, so in frequency domain, so first of all, your effective sample rate is expanded, right, by a factor of m, right? Because now you take one every m samples, right? So in between it's like m times capital T. So far so good. And second thing that would change would be all these omega factors, right? Because I multiply by a factor of m in time, so in frequency domain, what should I do? So divided by m, right? So it's inverse. Okay, if you forgot about this, so this is supposed to be the signal processing course that you probably took in the first 2 years of your undergrad program. Should be, if I remember correctly. Yeah, so if you forgot, it's okay. Now is the time to kind of review. All right. So in frequency, right, these factors, you need to divide it by a factor of m. All right, let's look at the example, right? Let's start from the easiest example, right? So m equal to 2. Actually, can m equal to 1?
Yes.
Then basically no downsample, right? So you can downsample by 1. Basically, you didn't do anything. Okay, so that's why the smallest number is m equal to 2. Okay, so this is your original spectrum. And when it says spectrum means the discrete time, right? So for the discrete time, this is repeating at every 2 pi, right? Remember? Okay, I assume that you take out that physical time, so you become a digital samples. So that's why it's 2 pi, 4 pi, 6 pi, so on and so forth, right? All right, so that's the original x of omega. What happened to xd of omega, the downsample factor of 2? So go back to this. You see all this omega factor as divided by 2, right? And of course, the scaling factor here also goes down, so it become your height also reduced by a factor of 2. All right, how should I draw this spectrum? So this divided by 2, what do I get? So okay, let's start from the easiest. Do I have a copy at 0?
Sure. Yeah.
DC? Sure. So what's my next copy? The next copy should be at 2 pi, pi, or 4 pi.
Pi.
Pi. Okay. Okay. All right. So I think what you guys probably get confused a little bit here is that yes, here the sample rate effectively divided by 2, right? Omega s over 2. That's the new sample rate, effective sample rate. Okay. So now let me ask you. Omega s over 2 is a sample rate, right? So imagine I take out that physical unit, I turn that into digital sample, your digital domain. Omega s over 2 correspond to pi, or 2 pi, or 4 pi. one thing to think about is that, you know, we've been talking about this, how we convert from analog to digital, right? Right? Remember that picture? Let me see if I can find it. Here. Remember this? Remember this? So in analog and some sample rate, right? Sorry, this is a sampling function, and after sample you repeat it omega s, right? Whatever the sample rate. So this corresponds to 2 pi. If I downsample it, yes, the sample rate effectively reduced. So let's say omega s divided by 2. What does omega s divided by 2 correspond to? Pi, 2 pi, 4 pi, 6 pi, 7 pi. The new sample rate. Okay.
It depends on how you're seeing the time domain.
Yeah, so the time domain, effectively I'm asking you, okay, if I sample at 2 kilohertz, you sample with analog signal, right? At 2 kilohertz. And you go through this, and you whatever that 2 pi correspond to 2 kilohertz, right? And now if I say that, oh no, I'm gonna sample at 1 kilohertz. You still take the sample, right? Correct? And you go through the whole process. You do DFT or FFT. In the end, what does that 1 kilohertz correspond to? 2 pi. If they say, hey, you know, Mike, I'm not happy, who cares about 1 kilohertz? I'm gonna sample at 5 hertz. Okay, so 5 hertz. I'm gonna sample analog signal at 5 hertz. At 5 hertz, if you go through this process, that 5 hertz corresponds to still 2 pi. Okay, I know this part can be a bit confusing. You know, I myself got confused when I was a student. That's why I slowed down here a little bit. Okay, just remember, whatever that discrete time, that sample rate, right? Whatever that sample rate that you're gonna fix at, when you convert to the digital domain, you do FFT or DFT, that always corresponds to 2 pi. All right. After we detour this much, so now here, where's the next copy? So 0, you guys agree, right? At DC, you should get 1 copy. So where's my next copy? To the right. 2 pi. To the left, I'm sure that you will know minus 2 pi.
But this downsampling we are doing after the digitization of the original sampling rate, right?
No.
So how will it map again to 2 pi? Because it will only map to 2 pi if we
So look at this picture.
quantify
If I take this, downsample by m, in the physical world, what's the difference between I use another ADC and I do the F clock divided by m? Is there any difference? Physical. Just look at this. Yeah, so that's actually a very good question. Look at this, right? If I just duplicate another ADC, I sample exactly the F clock divided by n to begin with, what's the difference at the output? Of course, you know, you say, hey, Mike, you are cheating. You know, you just told us that, you know, ADC design is higher speed, is more difficult. Yes, I agree. Right now, we are in a signal processing. We're gonna assume everything is perfect. You're gonna design a perfect ADC, right? You take this class, in the end of the day, you're gonna design a perfect ADC. Okay? So, does everybody agree there's no difference? If there's no difference, then what I just said is still valid. Why do I carry sample at 2 kilohertz, 1 kilohertz, or 5 hertz? They all correspond to 2 pi. All right, yeah, I know it's a little bit confusing, you know, because you just like you said, right? That's also how I get confused when I was a student. I was like, you know, what do you mean? You know, you create something already at digital, right? And you do that as if, you know, 2 pi should divide by m. Kind of, right? So. All right, so here, what should we do? 0, 2 pi minus 2 pi. Okay, so how do I draw this? still a triangle or hexagon or square wave? Half height? Half height, everybody agree? Okay, very good. I agree. Yeah. All right, so what is this shape then? Triangle, square, trapezoid, or hexagon? What should be the shape? Diamond? No. This, right? Just math. X of x omega over 2. Okay, so you should retain the same shape. Okay, so triangle is your triangle. Yeah. All right, so I'm gonna draw a triangle. It's just that you know where's the left and where's the right. Do I copy the same triangle and just scale down this? Yes. No. Do I draw a triangle here and then just align this maximum here and minimum here? That's my new triangle.
Those heights and bottoms don't.
Okay, so we have one proposal. So your height scale lower, and your width, so basically your base, shrink by a factor of 2. Okay, everybody agree?
I guess it might be the opposite.
Maybe the opposite. Okay, so we have a second proposal. So what's your proposal? So
The height shrinks by half and the width grows by the times 2.
times 2. Okay, so 2 proposals. Any other proposal?
The width is the same, but the amplitude is.
Oh, okay, yeah, that's correct. Yeah, third proposal. Yeah. 1, 2, 3. We go by democracy and we should vote. All right. The answer is yeah, you should expect. Yeah, let's just go by math, right? Because you can see 2x of the original omega, so now it's in radian, right? Corresponds to the original waveform. Yeah, so that's why it's expected. It's okay. I'm pretty sure that you guys already went through this in your undergrad class. Yeah, you just forgot. Just like when I was a student, I also forgot. It's okay. Yeah, just use this opportunity to review the knowledge. All right. So this. Very good. Okay, so this is a downsample view. Your signal become wider and your height could become smaller, but by and large it still looks good, right? It's still like discrete time or digital signal repeated 2 pi. All right, so let's continue this exercise. Except that now I'm gonna do a factor of 3, okay? So factor of 3, what should I do after downsample? First of all, the height become 1/3, right? So now it has to be even lower, right? 1/3. How about the base? Wider, 3 times, right? 3 times wider. This. Okay. There you go. Are we happy or we're not happy?
Not happy.
Not happy. Why is it we are not happy?
Idiocy.
Idiocy, right? You see, whenever you have things to collide with each other, right, like this, you knew that you cannot recover back, right? So. Okay. What is that idiocy in this case? When was the last time we saw such idiocy?
When you're not following the next.
Okay, we are not meeting the Nyquist theory. Okay, very good. So tell me why here. Why are we not meeting? Is it true that if we downsample too much, we are not basically not meeting the Nyquist theorem? Does everybody agree? right? Actually, you know, earlier I mentioned that this system is equivalent to ADC, but sample at the lower rate, right? So if you keep downsampling, at some point, it's effectively your sample below Nyquist rate. If you sample below Nyquist rate, Nyquist already told us you can like cause distortion, you can like alias, you can uncover. Okay, so that's exactly what's happening. Okay, so what do you do, right? So typically, what you need to do, you need to apply some kind of a pre-filter, right? Some kind of pre-filter. So let's say if you wanna do downsample by factor of 3, right? So this pre-filter, you know, I'm not gonna assume that's ideal filter, okay? So these breakable filters. What is the upper bound and lower bound? What is this frequency I should set to? So that, you know, after I downsample, it will not overlap with each other. What's that magic cutoff frequency? Again, I'm trying to avoid this scenario, okay? I'm trying to avoid things are sitting on top of each other. What should I do?
Twice the path?
So what is this corner frequency that I should set to for the m equal to 3 case? So that after I downsample, I don't want that to overlap.
Oh, pi over 3.
Pi over 3, thank you. So pi over 3. Why is that? Pi over 3?
Because then when it expands, it stays within your bounds.
Exactly, right? Pi over 3, you expand by factor of 3. So pi over 3 will expand to pi. And then this minus pi over 3, after expansion, it go to
Minus pi.
minus pi. So you're not touching each other. Okay, so. All right, so if you do this, of course, after you scale the height, and then you should see them apart, right? So these two pi, these pi. All right, so this is how you can avoid. So does this look kind of funny? A little bit? By the way, this is correct, yeah. So you should actually set the bandwidth to pi over 3 to minus pi over 3, and you put it as filter, right? It's basically like an anti-aliasing filter, right? You think about it, right? But then you say, hey, Mike, yeah.
But there's no difference between what we see, I guess.
Is that true? Because here, you see those two are adding to each other, right? You kind of, because you overlap, so you're gonna add. Yeah, so you kind of have some superposition. Yeah. But if you do pre-filtering, is there anything I'm adding on top? Nothing, right? All right, but then it also doesn't look very good, right? This doesn't look like a triangle. So what's going on here? So I cut out, because I know this part, you know, you're gonna overlap, so I'm gonna cut you out so that after you do downsample, there won't be any overlap. On the other hand, this also does not look very good. So what does this mean? Basically, what you are seeing here is real. Yeah, so indeed, this does not match the original triangle wave, right? So what this means is that if you insist to do downsample by a factor of 3, basically what this tells you is that your original signal, you cannot support this bandwidth to begin with, right? So our original triangle is supporting between pi over 2 to minus pi over 2. It's too wide. It's too wide. So the only way for me to accommodate this kind of input, right? If you insist you want to downsample by 3, I basically need to cut out this portion. Yes, you know, whatever that signal you get lost, it will be lost. Okay, it will be lost. So So typically when you design a system, you need to make this kind of decision, right? So if let's say, hey, you design a system, some system, you know, they can tolerate this kind of loss of the information, just a tiny bit in the higher frequency, maybe you are fine. Just cut it out, at least you know you can avoid those aliasing. Okay. But if you think that you cannot even tolerate that, you should actually discuss with your colleague system design, say, hey, please don't downsample this much. Basically, this is what I mean. Sometimes, you know, when you do this, you know, even if your signal is strictly within pi over 3 and minus pi over 3, but as you can imagine, there may be some unwanted signal after beyond this pi over 3 and minus pi over 3, right? So maybe there may be some blocker signal, right, interference signal out there. So having this pre-filtering actually would be helpful, right? Because you're gonna protect the signal, which is actually pi over 3 to minus pi over 3. It's just a little bit unwanted signal outside. You're gonna remove that. Because you know, if you don't do that, you know, after downsampling, you're gonna have this ADC. Okay, so this pre-filtering is very important. So every time people do downsampling, they must do this pre-filtering. Okay, so those two are together. All right, so when you put the filter, so this in this picture, right? So you have the original discrete time signals or digital signal. So let's say coming from the ADC, and then you say, hey, I want to do downsample, right? Trifecta of M. And before that, you need to do this pre-filter, right? So that in this case, there will be a low-pass filter. So this is a must-have sequence. So you do the filtering, then you do the downsampling. Basically, you drop the sample, right? The downsampling is actually very easy if you think about it, right? You just take one, and then ignore the rest. Take one, ignore the rest. Take one, ignore the rest, right? Very simple, right? So in digital, downsampler is very easy to implement. It's just that, you know, before that, you know, you better to have a cutoff at pi divided by n, okay, to avoid the aliasing. All right, so this sequence, you know, combining the filter together with the downsampler, this has a very special name. In the future, you're gonna hear this all the time. This is called decimator. Right? So in the future, whenever you hear people talk about the decimation, decimators, basically that means that you should have a pre-filtering plus the actual downsampler. Okay, so this is the pre-filter. And you can think of that as an anti-aliasing filter. All right, so that's the decimator. So you filter and then you downsample. Next, we're gonna do the opposite. All right, so we're gonna do something called upsampling. So symbol-wise, you can see we reverse that error direction, right? So before we do a down error, and now it's up error. So this is factor of L, and in this case, you know, effectively you increase the sample rate, right? So that's why the sampling period here is shrink. So which means your sample rate increased by factor of L. Okay, and in this case, you know, you would also put another filter, and later on we're gonna see why. Okay, but to begin with, let's try to understand what this upsampling is doing. So you have a discrete times signal, right, or digital sample, right? So you will come in maybe like this. So maybe that's the original analog signal that you were trying to sample, right? Okay, so I want to increase the sample, right? I want to do the opposite. How should I do this? So the dashed line is, you know, the original analog signals, and this is the ADC, create all those samples. And I want to create something in between.
I assume two ways you could do it is if you just simply copy the sample that you had before, which one would be very accurate, or if you wanted a more accurate upsampling, you could have another ADC and put it off phase.
Okay. Okay, then I think that's a thought. Yeah, but typically we don't have another ADC, right? Because you buy this sensor, whatever that give you is whatever those samples, right? You cannot ask Tesla to say, oh, by the way, I want you to install another sensor, another ADC to give you more samples. So usually you don't. All right. So basically, what you can work with is the information that you already have. So what she just proposed, may be actually a feasible way of doing that. But before we do that, usually what people do for the upsampling is that you create a zero sample. Okay. So because I don't know anything, I just say, yeah, there should be a sample, and I don't know anything. I'm just assume that's a zero. So you're gonna have this 1 here, 0, 0, 0. 1 here, 0, 0, 0. So you're all 0 in between. Okay, so upsample by factor of 4. So I need to insert another 3 samples. Okay. So that would be starting point. This process, sometimes people call it as a zero padding. Why? Because you are just padding a bunch of zeros. Depends on your upsampling factor, right? Your upsampling factor is more, then you should obviously insert more zero, right? In between the original sample. Okay, so we're gonna mathematically express this. So x upsampler, so it's u of n is equal to x of n over L. And this is essentially xc of n t divided by L. Okay, so this x upsample of n, you are going to have this x of n over L when n equal to zeros, plus minus L, plus minus 2L, right? Because those are the actual original sample, right? What I drew on the top. But in between they are all zero, right? In between they are all zero, so it's elsewhere. They are all zero, right? So mathematically, this is how you express this. So only when you are integer multiple of capital L, right? Then that's where you have all these samples. Otherwise, you are all zero. Okay. So now we're gonna do the same thing. This is a time domain view, and we're gonna look at the frequency domain view. Okay, the frequency domain view. We're gonna do DTFT, discrete time Fourier transform. So this upsampled spectrum is sigma minus infinity to infinity. To express this upsampled signal, so you have a value when n is an integer multiple of L, but elsewhere are all zeros, right? So there's a math function called delta function, right? Delta function is when you have hit to particular value, you're gonna have some value, the finite value, otherwise it's all zero, right? So we're gonna express that. So it'd be k from minus infinity to infinity. That's okay. Delta function n minus kl. So basically only at integer multiple of capital L, you're gonna have a value. So this is the upsample, and you take minus exponential to the power of minus j omega n. Okay, and because that's a delta function, so n has a value only when you are integer multiple of L, right? KL. Okay, so only when n is integer multiple of L, you have a value. So that means that all the rest of it, they are all zero, right? So we can take them out. So it's only when n equal to k times L, right? So you can plug that in. So you can remove basically most of the term, right? Look at n from minus infinity to infinity, but most of them are zeros. Only when n is k times L has a value, so we're gonna take out that first sigma. So what you are ending up with is k from minus infinity to infinity, x of k, right? When n equal to kl, and then you still have this exponential function minus e to the power minus j omega n. And we know that n has a value only when they are kl. Okay, so this is just an algebra manipulation. Okay, so you look at this. This is exactly doing the yes.
Sorry, x of what? Kind of
K.
looks like a k and then.
Okay, yeah, it's okay. So x of k times exponential function. Okay, so this looks exactly like a DTFT, you know, except that the frequency here is omega times L, right? You still have a k here, right? So essentially what you get is that the original, as if the original spectrum here, you have E, J, omega L. This is called frequency scaling. Okay, it's all the frequency scaling. All right, so with this, what happens is if this is the original analog signal, and the second column, second row there is the sampled discrete time signals, and now you're gonna compress. It's like you pressed it, okay, by factor of n. All right, so in this case, L equal to 2. That's our case here, right? L equal to 2. So you're gonna compress by 2x. Yes, the whole spectrum still repeat every 2 pi. As we said, you know, your discrete time signal, it should always be true. However, because you compress here, you do have something that show up at 2 pi divided by L. Okay, so L equal to 2, that means that you have something happens, you know, at pi in this case. So that doesn't look very good because we know if you upsample the signal, ideally what you want is as if your ADC, right, your ADC sample at f clock times L, ideally speaking, right? Just like downsample is, remember I said that it's equivalent to ADC you sample at f clock divided by M. Okay, so just imagine that's my goal. I want to do that. But now, when I do the zero padding, there's no information there. And that's why you have this extra copy show up here, which is kind of reasonable, because there's no way close to the original signal, remember? The original signal is more like this dashed line on the top. Even visually, you understand that, you know, if you create the zero here, there's no way close to the actual analog signal, right? So in the frequency domain view, basically what this tells you is that this extra copy show up in the pi in this case. That's why it's explained why you are nowhere close to the original analog waveform. Okay, however, this one does give you a very good hint. What is the hint? If you look at this, yeah, you know, this is actually not too far away from the original analog signals, you know, and I still have a copy repeated 2 pi. There's only one copy I'm not happy with. What is that copy?
The one between
The guy in between. I need to get rid of it. Right? As simple as that. How do I get rid of it?
Do a low pass filter.
Low pass filter. Very good. All you need to do, you want to select this. Right? And this is digital, right? So when you do the digital filters, you know, when I create a low pass here, do I also have the same low pass at 2 pi? Yes? Because everything repeat, right? Everything repeat. And then you get another thing minus 25. All right, so that's our goal. You want to get rid of this unwanted copy, and you just want to select the one you actually wanted. All right, don't worry, I do have one slide for you. Okay, so exactly like this. But you guys already suggested, right? So you have these low pass filters and repeat every 2 pi, and you select the spectrum that you actually want, and the other guy just out. So look at the end spectrum. You have the original triangle waveform, and you have another one repeat at 2 pi, and nothing else. So let me ask you, this spectrum, so let's go back to original view, right? You have an analog signal, you put an ADC. Do you believe that this spectrum is equivalent if I sample that ADC at f clock times L? Basically, you sample at faster rate, right? Instead of 1 kilohertz, maybe if I upsample by 10, this is equivalent to you sample at 10 kilohertz. If I sample at 10 kilohertz, this corresponds to 10 kilohertz, right? And then if my original signal physical bandwidth remain the same, before I sample at 1 kilohertz, now I sample at 10 kilohertz, the spectrum here, the base here, will be smaller or will be wider? Smaller. Smaller, right? You say smaller. You see this what tell you is smaller. Pi divided by capital L, right? So everything comes back, and that match exactly what happened in the physical world, right? So that kind of prove or validate that, this whole process is actually correct. Okay? All right, so we're done. So upsampling, just that simple. Zero padding. You want to upsample more, just pad more zeros. You do that, and you know that there's nowhere close to the analog signals. What you do is that, we call that as a, sometimes people call that as an interpolation filter, right? You do this, you get rid of the one that you don't want, and you get eventually the waveform as if you sample at a higher rate. Okay. So what does this ideal interpolation filter does, right? So I know in the spectrum is clear, right? So we get rid of the unwanted copy, but let's look at exactly what they are doing in the time domain. So this is the example again, upsample by 5. So that's why you see 4 0, right, in between the original sample, right? So far so good. So all the filter that we are trying to apply here is nothing but filling the gaps here. You see, because your original signal cannot be one sample and go back to 0, right? In analog world, is there any signal that looks like that? You need an infinite bandwidth, right? So there's no way that any physical analog signal would look like that. So it's all about how you fill in the gap in between, right? So if let's say you do this ideal breakable filter, right? So this is breakable filter. To do the interpolation, what is that impulse response of a breakable filter? It will be a sync, right? It will be a sync, yes. So you'll be doing the same thing as what we discussed before. You take all this and then multiply by all this single function, and then you need a lot of samples, right? So it turns out that it's not that convenient. It's too complicated to do all that, right? So you can make some compromise. You can make some compromise. So for instance, in between the samples, right? In between the samples, you can just draw a line here, right? And then you get the dots here, 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 here. What is this called? What kind of interpolation?
Linear.
This is called linear interpolation, right? So remember in, I don't know, middle school or high school, right? Or even elementary school, that's what we learn, right? When the first time you learn about interpolation, probably the school teacher that's just teach you, yeah, just do this way. Turns out that's one of the interpolation filter. Okay, so now even just visually, look at this. Is this perfect? This is not perfect, right? Is it simple? Yes, it's simple, right? So you just need to draw the line, right? Even the middle school kids, they know how to do this, right? So it's simple. Computation-wise, it's simple, but it's not perfect. Why is that? So it turns out that if you do this linear interpolation, this is the filter response. Okay, so this is the filter response in frequency. Okay, it will look like a sinc function. Okay, you look like a sinc function. So that means what? That means that actually I do have this picture. Okay, so let me show you this picture first. Okay, so this is upsample by 5, and if you want to do linear interpolation, basically you should come up with this triangle impulse response. Okay, if you do that, essentially you're gonna get this linear interpolation between the two, right? So I think when you do interpolation, you do what 1/5 of this and 4/5 of this and 1/5 of this, right? How do you do linear interpolation? And if you are in the here, so you have 3/5 of this and 2/5 of that, right? So that's how you do the linear interpolation. And that happened to be exactly like this. You see all these coefficients, 1/5, 2/5, 3/5, and 4/5. If you do a convolution, that's exactly what you got. Okay. So that's no problem. And like I said, if you do this impulse response, you do DTFT, and you get this sinc function. Okay. So that means that, look at this picture. Instead of having this breakable filter, you're gonna get some sinc filters. So here's a question: can I get rid of this completely? You cannot, right? Is this attenuated? It's still attenuated. So that's why even visually, do you agree that if I interpolate like this red, this signal will be closer to like this. I mean to the original continuous time analog signal, right? You agree, right? So and that was the reason, because even though you are not perfect, you still attenuate those unwanted spectrum right in between, right? So it still help. So in the future, you very likely, or I should say, almost always, you will face this kind of, we call it the engineering trade-off. Okay, you want to upsample the system, you know that you cannot have that expensive processor to help you to do all this fancy interpolation. By the way, if you do care, by all means. Okay, you do care, you just need to work with your boss and say, hey, this is very important, we cannot accommodate that kind of loss, so give me the resources, right? Give me the best processor, right? And I'm gonna compute, I'm gonna have the best interpolation filter.
What will be the application of upscaling if you're not gonna get the information at that higher
perfect.
frequency?
Yeah. So this is what I said last time, right? So if you have different signal stream, if you want to align the signal information, right? And then you say, hey, you know what? Unfortunately, I cannot just downsample because I'm gonna violate the Nyquist information. Then the only way to align them is you upsample the slower one, right? This is slower, right? So you have some sensor, give you fewer samples. But in order to align with another higher stream, data stream signals, you need to upsample the slower path, right? So that could be one scenario. But you're right? So when you do this, depends on how you choose your interpolation filters, you're gonna end up with some loss. All right, so that's you're gonna have a bunch of engineering trade-off, right? So you need to investigate this at right now what I'm teaching you is, you know, how that all that works. So in the future, hopefully when you face this kind of difficult situation, at least you know how to deal with them, right? You know, stop make decision that, oh yeah, you know, this is how we should do this filter. Okay. All right. So now we talk about upsample and downsample, right? And you obviously can see that, you know, no matter how I do the downsample or upsample, it's always an integer number. Integer number. Can I do a non-integer number?
Sure.
Okay. So can I, for example, I want to change the sample rate to 2/3.
Yes.
Yes,
you can.
Okay. Yes. Very good. As long as you know you can express that as a fraction, right? So like this, m and n, right? You know you can upsample and downsample, right? So basically it's just like that. Yeah. So you can just upsample and downsample. Yes, you know, when you do upsample, downsample, it has to be integer numbers. But you look at the ratio, it doesn't need to be an integer number. All right, very good. Should I downsample first and upsample, or upsample and then downsample? Is there any other option? So option 1, up and down, right? Option 2, down and then up. Or you say that, Mike, you know, you're just confusing us, you know, they are the same.
Maybe you lost more information if you're down first.
Does everybody agree, right? She was saying that, okay, so if, let's say, I want to do, what is the number? So, how do I do this? If I want to change the rate to like this, originally is f clock, and now I want to go 3/10 of the f clock. Upsample by 3, down by 10. All right, so let's go back to her explanation. If I go down by 10x, and then up by 3x, what do I do? Remember, go down, you have something called decimator, right? Remember? What is a decimator do? You need to do a pre-filter, right? You need to do pre-filter. So you need to go down by 10x. That means that you need to have this pre-filter to be pi over 10, right? So that's we already talked about this. So you shrink the information by 10x, and then you say, okay, go up. Would that lose the information? You might actually. So yeah, so she's right. So go down is not a very good idea. Maybe you are lucky. Sometimes if you're lucky, you say, okay, my signal is so tiny anyways. So even if you go down by 10 and lose nothing, then in that case they are equivalent. All right. So let's do her proposal. So incoming signals, the sample period is capital T. You say up, right? So up. Okay. By the way, so here interpolation filter. Did I show here? Okay, yeah. So don't forget, right? So if I do upsample, you do upsampler, and then you have a low pass filter afterwards, right? That's the interpolation filter. This is interpolation filter. Okay, so far so good, right? Just like downsampling, you need a pre-filter, which is like anti-aliasing filter. Okay, so let's just do that process. All right, so let's go for her proposal. We're gonna do up, factor of L, and then we need a what do you say? Interpolation filter, right? Interpolation filter. And by the way, we're just gonna assume for now just breakable filter. Okay, breakable filters. What is the corner frequency? Okay, so it's okay. Let's come back to this view. what's the corner frequency? What's the cutoff frequency for this interpolation filter? Pi divided by L, right? Yeah. All right, so that's pi divided by L. Okay, are we good? So the output here should be upsample stream. Then we're gonna do downsample. So how should I do downsample? Downsample, basically I should say decimator, right? Decimator. Do I do filter first or downsample first? Filter first. Okay, so let's do filter. And can you please remind me what's the corner frequency? So this we're gonna still assume that's a for both filters. What is this frequency? Okay, sorry, I haven't even told you what's the effective, right? Pi over n. Very good. All right. So what's the effective sample rate after all this exercise? The effective sample period. Yeah, I should say sample period is so before it's t, right? So now it's t times L divided by m or m divided by L. M divided by L, right? Am I right? This period, right?
Oh.
It's correct, right? Yeah, if that frequency, that's L divided by M. Okay. All right, we're done. So this basically gives you the non-integer conversion, the sample rate conversion. Okay. All right, can I simplify this system even more?
No. Yeah, you can combine the filters.
Okay, you can combine the filter. How should I combine the filter? So what's our new proposed system?
Whichever element is larger, you stop filtering.
So this thing in the middle will be condensed to only one filter, right? And what's this cutoff frequency?
Depends on whether the L is larger or L is
So minimum or maximum? Minimum of pi over L and pi over M, or maximum of pi over L and pi over M? Minimum. Very good. Okay, we're done with all the sample rate conversion. Going up, going down. Even if you want to go to integer, non-integer ratio, you can also do it. Any question? Okay, if not, let's take a short break.